Okay, good. Hello, glad to open the session for State Style. Today, I'm going to talk about the overviews of Near Protocol and its ecosystem. Before the start, I think you're wondering who I am. My name is Minji, and you can just call me MJ. I'm an undergrad student at EWHA Women's University, majoring in cybersecurity. I'm also a formal Zango crypto researcher, and here's my Twitter and Telegram, so feel free to reach out. Among all the roles and titles, I'm here as an external relations manager at EWHACHAIN. So what is EWHACHAIN? EWHACHAIN is the blockchain academy club of EWHA Women's University. Since 2018, we started as a small study group inside EWHA Women's University, and now the club is formed of hundreds of members and alumni with 40 active participants for this term. And we are growing as one of the most influential blockchain societies worldwide. We're expanding our connections more and more and making great performance. We're exploring various ecosystems and layers of blockchains, following the trends as fast as we can. Majority of EWHACHAIN members are contributing to the Web3 industry and deep diving into the blockchain. If you're, this was the brief introduction about me and EWHACHAIN. And if you want to know more about us, follow social channels of EWHACHAIN. We have Mediums, GitHubs, and Twitter, and more. And we are very active and trying to communicate with others always in every way. So feel free to reach out, and you can check more about EWHACHAIN by scanning this QR code or clicking the link that Irene just sent. So let's start to explore NEAR. Have you ever studied about NEAR? How are you going to describe NEAR in one word? If I were you, I will say NEAR is layer 1 sharded proof of stake blockchain. Layer 1 means that NEAR is the main network within its ecosystem. So NEAR is a protocol which processes and finalizes transactions on its own blockchain. The transactions will be executed to parallel using the sharded architectures. NEAR protocol employs proof of stake as its consensus algorithm. Because the blockchains with monolithic design solutions are tended to be an Ethereum killer, NEAR has been developed with a focus on performance and usability, both for developers and various kinds of users. The strengths of NEAR include technical innovations, user-friendliness, fast and cheap transactions, eco-friendliness, and great developer experience. Let's take a look at this more in next slides. NEAR protocol consists of some technical innovations. First, NEAR creates high performance with the sharding architecture. Sharding is a blockchain scaling technology that divides computation across parallel shards. This makes the protocol scales infinitely and resists short-term usage spike. Also, NEAR has trustless bridge that is interoperable with Ethereum, so it's such a good solution of NEAR to interact with the top protocol with a high volume. Aurora is a remarkable project in NEAR that provides EVM-compatible development environment, so a developer who is familiar with Ethereum can easily deploy Solidity contracts on NEAR. Using these technical innovations like sharding, NEAR transactions are incredibly fast that each transaction can be executed in just 1 second with a low-cost transaction fee. This provides better user experience for end users. So let's talk about what makes NEAR user-friendly. NEAR uses human-readable accounts like alice.near. This is similar to the name service systems of other protocols, but NEAR provides this without the need to buy one. Also, NEAR doesn't require to install programs or browser extensions because it leverages a web-based wallet. Also, NEAR has simple yet rich system of access keys to handle account permissions. This is helpful to prevent the security issues on blockchain accounts. Also, NEAR is popular for its environment friendliness. The network is certified carbon neutral. In February 2021, NEAR protocol engaged with South Pole, a leading project developer and global climate solutions provider, for its carbon footprint. Also, using the efficient proof-of-stake mechanism, NEAR consumes the same amount of energy that Bitcoin consumes in 3 minutes in 1 year. One of the greatest strengths of NEAR is related to the developers or students like us. First, with NEAR, we can make smart contracts with programmable languages like Rust or even with JavaScript. Also, NEAR provides complete documentation, examples, lectures, and materials to study to make the developers and students easily onboard on its ecosystem. Also, the dev relations of NEAR holds office hours every week that anybody who has interests in NEAR can share their ideas and questions. And when a smart contract or DFs are deployed, the system gives 30% of gas fees to the developers. This encourages the developers to build on NEAR. Lastly, NEAR actively gives builders grant programs to help them to extend the ecosystem. So let's look at the NEAR protocol as a network. NEAR has a cloud-based infrastructure, but instead of being controlled by a single entity, the NEAR cloud is supported by independent people running their own infrastructure around the world, which means that NEAR is a community-operated cloud. There are 3 main actors in NEAR: users, validators, and the blockchain. The users consume the services provided by the NEAR network. Users can have one or more accounts. They transfer tokens such as the native token or community-built ones, and user can execute DApps stored in the blockchain known as smart contracts. And if a user is a developer, they can store their own decentralized app in the blockchain. The validators operates the computers that form the decentralized network. They are people distributed around the world, running the infrastructure that underlies the NEAR network. They execute the transactions sent by the users, persisting their outcomes in the blockchain. Also, they secure the network by overseeing the rest of the validators and the blocks they create. And blockchain, the NEAR protocol, works as a persistent storage for the network. So let's take a look at accounts and transactions, because these conduct key roles in NEAR. Its address system substantially differs from other blockchains like Bitcoin or Ethereum. It uses the term of accounts. Instead of identifying users by their public or private key pairs, it defines accounts as first-class entities. The first characteristic is NEAR uses human-readable accounts instead of using public keys of long string of random characters. It provides users to simply use words like name services on other protocols. Also, by using multiple key programs, we can control permissions on an account. Multiple key pairs with different permission provides a better security model for users, since loss of one key pair does not compromise an entire account and has a quite limited impact. And this allows to share individual keys with third parties, limiting their potential impact in your account and allowing to replace any compromised key. Accounts on NEAR have hierarchical accounts structure. It is useful when we want to manage multiple smart contracts under one parent account. Since they're stored on the blockchain, accounts are created using blockchain transactions. This is one of the difference between Ethereum, because generally Ethereum accounts have no need to create transactions to create account. Also, like the addresses of other protocols like Ethereum, NEAR accounts can optionally hold a small piece of software known as a smart contract. NEAR smart contracts are written in established languages as Rust or JavaScript. Now, let's wrap up throughout the comparison with Ethereum. Ethereum wallet uses public key using long keys, but Near uses short name for an account ID. Also, unlike Ethereum, which an account can only have a private key to control a program, Near provides multiple key pairs with permissions, so we can specify which key can control which role. That's why we call Near account as a permission-based key pair. Also, because the account is stored in Near blockchain, the transaction should be created to make an account. But accounts by itself won't get us anywhere. So it's the transactions that make things happen. Each transaction always has sender and receiver accounts, and it is cryptographically signed by the sender's key. Transactions in Near may contain actions that do asynchronous work. This means a cross-shard transaction that affects multiple shards is executed in those shards asynchronously. This makes the consequence of cross-contract call to make very different outputs. For example, a transaction contains a cross-contract call. It may be marked as successful, but the other contract execution might fail. Each transaction is augmented with critical information consists of origin, destination, recency, and uniqueness. Origin is a cryptographically signed by a signer, and the destination, also called intention, is the information that will be sent or applied to the receiver. Recency is defined by the block hash from recent block within acceptable limits for one epoch. Epoch means a unit of time when validators of the network remain constant, and it is measured in blocks. Uniqueness means that a nonce must be unique for a given signer access key. In Near, while there is only one transaction type, the transaction itself may hold different actions. An action is a composable unit of operation that, together with 0 or more other actions, defines a sensible transaction. Because for most practical purposes, transactions will have a single action included, so we can assume that transaction means action. Let's look at some examples of transactions. First, function call action is the most important action on the blockchain, and it allows us to call a function of a smart contract. Create account or delete account and add key or delete key are transactions that manages accounts and keys. Transfer is also an important action since the action is used to send Near tokens from one account to another, which is basic of any blockchain. Since Near is proof of stake blockchain network, stake action is needed to become a validator. Deploy contract action is used when you deploy a smart contract to a given account. An important thing to remember is that one account can hold only one contract, so the contract is uniquely identified by the account name. If we issue this transaction to an account which already has deployed contract, a contract update will be triggered. Smart contracts on Near are written in Rust and compiled into WebAssembly. Each contract has one or more methods that can be called via a function call transaction. Methods may have arguments provided, so each smart contract call includes the payload consists of account ID, method name, and arguments. There are two ways to call a method on a smart contract. First, issuing a function call transaction. This will create a new transaction on the blockchain, which may modify a contract state. Second, the view call using read-only methods, which doesn't modify the state of data on blockchain, so this doesn't make a transaction. This is used with RPC nodes which the NEAR protocol provide a special API. So we reviewed which data are going on here. So let's take a look at how they will be executed through overall network. Instead of running only one blockchain, NEAR run multiple and call each blockchain a shard. So we should know about the sharding solution to understand NEAR. Each shard will have its own set of validators who verify transactions and produce blocks. The shards never communicate with each other. So let's think that system comprises 10 shards. The first challenge is that each shard having its own validators. So each shard is now 10 times less secure than the entire chain. Let's say there is 100 validators across 10 shards, meaning that each shard now only has 10 validators. And non-sharded chain with bad validators decides to hard fork into a sharded chain. Then attacker only needs more than 5.1 validators to take over the chain. Also, the question of who chooses validators for each shard is important too. Almost all sharding designs today rely on some source of randomness to assign validators to shards. Randomness on blockchain on itself is a very challenging topic. The partitioning aspect of sharding, however, raises a significant potential problems. Without downloading and validating the entire history of a particular shard, the participant cannot necessarily be certain that the state with which they interact is the result of some valid sequence of blocks, and that such sequence of blocks is indeed the canonical chain in the shard. These are the problems that doesn't exist in a non-sharded blockchain. So I'm going to share how Nightshade, the sharding solution of NEAR, can break and what attempts have been made to address it. In sharding, model the system as a single blockchain in which each block logically contains all the transactions for all the shards and changes the whole states of all the shards. Physically, however, no participant downloads the full state or the full logical block. Instead, each participant of the network only maintains the state that corresponds to the shards that they validate transactions for, and the list of all the transactions in the block is split into physical chunks, 1 chunks per shard. Under ideal conditions, each block contains exactly 1 chunk per shard per block, which roughly corresponds to the model with shard chains, in which the shard chains produce blocks with the same speed as the beacon chain. However, due to network delays, some chunks might be missing, so in practice, each block contains either 1 or 0 chunks per shard. But the sharding solution of NEAR, Nightshade, challenges to solve 2 major problems with existing approaches, which named state validity and data availability that is related to the formal problems. Nightshade moves NEAR from a single chain blockchain to a shard in terms of design or status, but not in terms of validator responsibility. This means that everyone qualified as a validator validates all the transactions together, but the network itself is split into shards. In Nightshade, there are 2 roles, block producers and validators. The block producer downloads the state of the shards they are assigned to before the epoch starts, and throughout the epoch collects the transactions that affect the shard and applies them to the state. For each block on the main chain and for every shard, there's one of the assigned block producers to who is responsible to produce the part of the block related to the shard. The part of block related to the shard is called a chunk and contains the list of transactions for the shard to be included in block, as well as the Merkle root of the resulting state. Block will ultimately only contain a very small header of the chunk, namely the Merkle root of the all applied transactions and the Merkle root of the final state. Throughout the rest of the document, we often refer to the block producer that is responsible to produce a chunk at a particular time for a particular shards as a chunk producer. Chunk producer is always one of the block producers. The block producers and chunk producers rotate each block according to a fixed schedule. The block producers have an order and repeatedly produce blocks in that order. Since chunk production, unlike the block production, requires maintaining the state, and for each shard only, some block producers maintain the state per shard. Correspondingly, only those block producers rotate the create chunks. To ensure data availability near use, an approach similar to that of Polkadot. Once a block producer produces a chunk, they create an erasure coded version of it with an optimal block code of the chunk. They then send one piece of erasure coded chunk to each block producer. Near compute a Merkle tree that contains all the parts as the leaves, and the header of each chunk contains the Merkle root of such tree. The parts are sent to the validators via one-part messages. Each such message contains the chunk header, the ordinal of the part, and the part contents. The message also contains the signature of the block producer who produced the chunk and the Merkle path to prove that the part corresponds to the header and is produced by the proper block producer. Once a block producer receives a main chain block, they first check if they have one part message for each chunk included in the block. If not, the block is not processed until the missing one part messages are retrieved. Next, if all the one part messages are received, the block producer fetches the remaining parts from the peers and reconstructs the chunks for which they hold the state. The block producer doesn't process a main chain block if at least one chunk included in the block they don't have the corresponding one part message, or if for at least one shard for each which they main the state, they cannot reconstruct the entire chunk. For a particular chunk to be available, it is enough that certain number of block producers have their parts and serve them. Thus, for as long as the number of malicious actors doesn't exceed certain number of one chain that has more than half block producers building it, can have unavailable chunks. Then now let's take a look at how transactions is processed through the Nightshade. The chunk producers only choose which transactions to include in the chunk, but do not apply the state transition while they produce a chunk. Correspondingly, the chunk header contains the Merkle root of the Merkleized state as of before the transactions in the chunk are applied. The transactions are only applied when a full block that includes the chunk is processed. A participant only processes a block if the previous block was received and processed, and for each chunk, the participant doesn't maintain the state for they have seen the one part message, and for each chunk, the participant doesn't maintain the state for they have the full chunk. Once the block is being processed, for each shard for which the particular maintains the state for, they apply the transactions and compute the new state as of after transactions are applied. After which they're ready to produce the chunks for the next block, they can compute new state. If a transaction needs to affect more than one shard, it needs to be consecutively executed in each shard separately. The full transaction is sent to the first shard affected, and once the transaction is included in the chunk for such shard and is applied after chunk is included a block. It generates so-called receipt transaction that is routed to the next shard in which the transaction needed to be executed. If more steps are required, the execution of receipt transaction generates another new receipt transaction and so on. It is desirable that the receipt transaction is applied in the block that immediately follows the block in which it was generated. The receipt transaction is only generated after a previous block is received and applied by block producers that maintain the originating shard, and needs to be known by the time the chunk for the next block is produced by the block producers of the destination shard. Thus, the receipt must be communicated from the source shard to the destination shard in the short time frame between those two events. The lifetime of the receipt is divided into two, producing and storing the receipts. The chunk producer for shard receives the block A, applies the transaction, and generates the receipt. The chunk producer then stores such produced receipts in its internal persistent storage indexed by the source shard ID. A chunk produced for a particular shard can only be validated by the participant that maintains state. They can be block producers, validators, or just external witnesses that downloaded the state and validate the shard in which they store assets. In Nightshade, once a block is produced, the chunks were not validated by anyone but actual chunk producer. In particular, the block producer that suggested the block naturally didn't have the state for most of the shards and was not able to validate the chunks. When the next block is produced, it contains attestations of multiple block producers and validators, but since the majority of block producers and validators do not maintain state for most shards as well, a block with just one invalid chunk will collect significantly more than half of the attestations and will continue being on the harvest chain. To address this issue, we allow any participant that maintains the state of the shard to submit a challenge on-chain for any invalid chunk produced in the shard. Once we assume that the shard chunks can be invalid and introduce a challenge period, it negatively affects the finality and thus cross-shard communication. In particular, the destination shard of any cross-shard transaction cannot be certain the originating shard chunk or block is final until the challenge period is over. One of the important characteristics of NEAR is validators. This is designed to reduce the probability of adaptive corruption by hiding which validators are assigned to which shard. The idea is remotely similar to the way algorithms. To not reveal the validators that are assigned to a particular shard, NEAR used two ways. First, VRF to get assignment. At the beginning of each epoch, each validator uses VRF to get a bit mask of the shards that the validator is assigned to. The bit mask of each validator will have SW bits. The validator then fetches the state of the corresponding shards, and during the epoch for each block received, validates the chunks that correspond to the shards that the validator is assigned to. Second, sign on blocks instead of chunks. Since the shards assignment is concealed, the validator cannot sign on chunks. Instead, it always signs on entire block, thus not revealing what shards it validates. Specifically, when the validator receives the block and validates all the chunks, It either creates a message that attests that all the chunks in all the shards the validator is assigned to are valid, or a message that contains a proof of an invalid state transition if any chunk is invalid. To build a NIR, you should know about what networks that NIR provides. These networks each operates their own independent validators and unique state. Mainnet is used for production-ready smart contracts and live token transfers. Testnet is a public network and the final testing network for near core changes before deployment to the mainnet. Betanet is a public network where near core is run to test its stability and backward compatibility. So it has daily releases with protocol features that are not yet stabilized. And local net is intended for developers who want to work with the NIR platform independent of the public blockchain. So the developers need to generate nodes themselves and control it. NIR is native token used in NIR protocol. It has multiple use cases. First, NIR secures the network through staking. NIR is a proof of stake network, which means that resistance from various attacks comes from staking NIR. Staked NIR represents the decentralized infrastructure of servers that maintain the network and processes transactions for applications and users on NIR. Rewards for providing this service are received in NIR. Second, NIR provides a unit of account. It is used for processing transactions and storing data, including price computation and storage on the NIR infrastructure. The network changes transaction fees in NIR to process changes and transactions. Also, NIR is medium of exchange in the ecosystem. It can be used to transfer value between NIR applications and accounts. This means that applications can use NIR to change for various functions like access to data or other complex transactions. Entities can also easily exchange NIR between each other without the need for trusted third parties to clear and settle transactions. In NIR, which uses the proof of stake system, has ecosystem which have some roles for the token cycle. Validators provide compute, storage, and security in the network in return for rewards from the protocol. Developers build profitable applications powered by underlying infrastructure of the protocol. Users of applications and platform itself are driven by getting value out of this interaction. Token holders of protocol native token either for later usage or to provide liquidity. Protocol governance body. Entity is responsible for the development and governance of the network. This can be a DAO or non-profit foundation. There are a few ways applications and their developers can have business models on the blockchain. First, users pay a transaction fee and there is an extra that developers add to it. Second, users buying some items such as NFTs or token passes. Third, users paying a flat fee via subscription or another type of charging model. NIR already makes it easier for second and third option via access keys and different types of interactions between application and user. So we got through how NIR network runs. Based on tokenomics, NIR has its growing ecosystem. So here are some projects that are using infrastructures for themselves. Aurora is an Ethereum virtual machine implemented solution that makes a smart contract deployed on Near. For an Ethereum developer, Aurora gives an easy solution that they can just even change the RPC endpoint you interact with. It supports all tools available in the Ethereum ecosystem like MetaMask, Truffle, Hardware, and Remix. Thanks to Aurora's EVM, Ethereum native applications can seamlessly be ported to Near's L2-like network that is built as a smart contract on Near. Developers may enjoy familiar Ethereum tooling when working with their Solidity smart contracts on Aurora. The base fee of Aurora is Ether, which provides a smooth experience for DApp users. This compatibility with Ethereum is due to the features of the Near protocol, such as delegated proof of stake, consensus mechanism, and dynamic resharding named Nightshade, allow unprecedented transaction speeds and scalability in a fully Ethereum compatible environment. Aurora also developed a bridge for Ether and Near. So the Ether and Near Rainbow Bridge is a trustless, permissionless protocol for connecting blockchains. The bridge protocol removes the need to trust anyone except the security of the connected chains without getting approval from anyone else. The Rainbow Bridge allows any information that is cryptographically provable on Near to be usable in Ethereum contracts. Not only infrastructure projects, Near has some influential projects. These are a brief summary of services on Near. So Tracer is the first move to earn the app, with wellness having some parts of social-fi and GameFi elements. It is a Web3 fitness and lifestyle app with inbuilt NFT gaming and social-fi elements, where you can earn rewards in token or NFTs just by moving, such as walking, jogging, and running. And also, Near has its NFT marketplace like Minbase or Paris. So these are DeFi protocols. Ref Finance is a community-led, multi-purpose, decentralized finance platform built on Near protocol. Near also has its various DAO ecosystem. Sputnik DAO is one of the most famous DAOs in Near, and it is an infra to create funding and squat DAOs. For additional research, or if you want to develop a Near, I suggest you get through these materials. First, the official Near materials. The section of Learn, Developers, and some papers included is so nice resources to learn about the protocol. These are some workshops on Near Foundation for university students too, and there is Academy for Near in online. Figment Learn is also nice to learn Near because it summarizes Near well, and there's some developer resources like making the app examples. Also, going to an offline workshops like Boomless in South Korea is good option too. And it's good to read, always good to read others' article in Medium and Twitter. Yeah, thank you for listening. And this was the brief summary of Near protocol and its ecosystem, including some development concepts and references. Hope you learned more about Near from today's session. And again, stay tuned for EWHACHAIN. Thank you.